Jnanam paramam dheyam. Knowledge is supreme.
In this example, it is 1x, x square, x5. If just now what we worked out for was R5, right? Polynomials degree less than or equal to 5, 3. Same proof will work for 1x, x square, x cube, x4, x5 also, right? So, if I take all the powers 1x, x square, x cube, x4, x5, they are linearly independent, and this is only a subset of it. This is only a subset. So, this is a general fact. If you are given a set which is linearly independent, every subset has to be linearly independent, obviously, right? And if a set is linearly dependent, then a bigger set will be linearly dependent, right? Because there is a linear combination which is 0 here, so you can think it as a linear combination in the bigger set also, right? So, anyway, let us check it again. So, if this is equal to 0, right, C1 times 1 plus C2 times x plus C3 times x square plus C4 times x5 is equal to 0. Same proof I am repeating. If this is equal to 0 means what? This is a 0 polynomial on the right hand side. So, like powers, coefficients must be equal, and that means what? C1 must be 0, C2 must be 0, C3 must be 0, and C4 must be 0. Same reasoning, right? Okay. Let us look at this. 1. So, I am looking at all polynomials now. I am looking at the polynomials 1 x, 1 plus x square, and 1 minus x square. It is a linearly dependent set. Why dependent? If I want to show it is dependent, what should I do? Show some linear combination is 0, where not all the coefficients are. So, here is one produced minus 2 times 1 plus 0 times x plus 1 times 1 plus x square plus 1 times 1 minus x square equal to 0, and obviously here 1 is coming, minus 2 is coming, that is not 0. So, that is a linearly dependent set. Okay. So, that is how you will check something is independent or dependent in a abstract vector space. Now, we have defined independence, we have defined what is generation. So, something which is independent and generates, we call that as a basis of that vector space. So, what is the basis? It is a linearly independent set, and every vector, right, V is a linear combination, of course, finite only, right. So, S may not be finite, right, but it is a linearly independent set. Okay. And second, every vector V is a linear combination of some finite number of, the finite number may change, right. So, but S may not be finite, keep in mind. Now, things are becoming different from the normal. In normal, earlier when we had subspaces of Rn, everything was finite, right. So, no problem. Here what we are saying is a subset S which may or may not be finite is called a basis if it is linearly independent, 1, and every vector is a linear combination of elements of S. Okay. So, here is a theorem which will not be proven, that every vector space has a basis. For finite, right, in Rn we know every subspace will be having at the most n vectors, right. So, there are generators, maximum number is n. So, how do you get a basis there? You remove which are, you have got a set which is generating. So, remove those elements which can be obtained by linear combination of the remaining, throw that out, throw out whatever is left in the end, that will be independent and generating. So, that will give a basis. Or what you can do is start with a one non-zero element and go on adding something more, right. So, that they become remain independent and generates everything. So, that is another way of getting that basis. But here when it is say in Rx or vector spaces which are infinite dimensional, I have not defined dimension. So, let us not go into that, which are not finitely generated, How do you show a basis exists? Right. So, there vector space is not given, basis is not given, nothing is given. So, how do you show? We do not know what that addition is, what is the multiplication and so on. There is general theorem. Now, you see the abstraction coming in. So, one proves the theorem that whatever be the vector space, whatever be V, whatever be addition, scalar multiplication, you can always find a basis. So, what basis, the idea is or same of finitely generated. If this vector space is non-zero, that means there is some element in it which is other than 0. If it is only 0, then nothing to show anyway, right? 0 dimension, you can 0 element is there. If there is one non-zero element in that, whatever it may be, start with that. So, you have got one set, right, which is linearly independent, but it may not generate everything. So, you want to enlarge it, add one more, but how long you can go on adding? If it is not finitely generated, probably you will go on doing it. When do you stop? How do you stop? So, the concept of infinite comes into picture, right. So, it relates to some basic things in set theory, which I can't go into it. So, this is a theorem which relates with some basic concepts in set theory. Okay. So, so this theorem can be proved that every vector space, but again there are issues there, because one uses some axiom in set theory called well ordering principle, which some mathematicians accept, some mathematicians do not accept. It is axiom. If you assume that axiom, you can prove this theorem. If you do not assume, you cannot prove or disprove this theorem. So, here is something new coming to you in mathematics, that there are theorems which are dependent on what axiom in set theory you are starting. It is like a game. Mathematics is like a game being played. It is like a football game or cricket game, right. If different set of rules, something else may come out. So, there are various formulations, axioms of set theory, in which what is something called well ordering principle is not a part of standard set theory. Okay. 90% of the mathematics assume that axiom and go ahead, you can prove this theorem. For others, unless you construct one, right, a set which is generating it, I won't believe it, kind of thing, right. So, anyway, so we will assume it that every vector space has a basis. Once that is done, if it is finite, so there are two possibilities, it is finitely generated, it is infinitely generated. If it is finitely generated, then one can prove a theorem that any two bases will have the same number of elements. If it is finitely generated, right, that means there is a finite set S which will generate, which is linearly independent and will generate, right. So, finitely generated implies that any two bases will have the same number of elements, and that is called the dimension of that finitely generated vector space. If it is infinitely generated, we say it has an infinite dimension, it is infinite dimensional vector space. So, in vector spaces there are finite dimensional, there are infinite dimensional, right. So, let us because it is the here itself, let us show that R x. Okay. So, let us look at examples. So, R n x is finite dimensional. Dimension of this, what is the dimension of this? We got a generator, right. For R 3, what was generating set? 1 x, x square, x cube. How many were there? 4 of them, and they were linearly independent. So, polynomials of degree less than or equal to 3 is a finitely generated vector space of dimension 4. So, this is of dimension n plus 1. So, what will be a basis? 1 x, x square, x to the power n is a basis, right. Let us look at R x. for this was the generating set. Right. So, if this is so, then L S or the span of S is equal to R x, and we showed S is linearly independent also. Just now we showed, right, it is linearly independent. Is it okay for everybody? It is linearly independent. Yes, because if I take a linear combination, right, just now we showed alpha 1 p 1 plus alpha 2 p k equal to 0, the left hand side will be a polynomial which is 0. So, all scalars must be equal to 0. Okay. So, this is also a basis. So, this S is a basis, and hence dimension of R x is infinite. So, that is an infinite dimensional vector space. Is it okay? Because we have got a set of generators which is not finite, and they are linearly independent and generate also. So, something that generates and is linearly independent is a basis. So, this is a infinite, S is a infinite set which is linearly independent, and it generates the whole of R x. So, it is a basis, and hence dimension of R x is infinite. You can call it infinite. Infinite is not, what is infinite is again a question. Say dimension is 3, 4, 5, 10, 1 million. What do you mean by saying dimension equal infinite? Dimension is a number essentially you think of. On the right hand side you are writing the word infinite equal. So, you can't write equal to infinity, because infinity is not defined as a number as such. So, it is better to say it is infinitely generated, right, or it is infinite dimensional, whichever way you want to call it. Okay. So, this is polynomials of degree less than or equal to 5, its right. So, its dimension is equal to 6, 5, 6 elements constant, okay, and R x itself is infinite dimensional, right. That set forms a basis for it. Okay. So, dimension is clear for a vector space. Okay. More examples. We have all come across this. R 3, they are finitely generated. I j k standard basis 1 0 0, 0 1 0 and 0 0 1. In R n, the same thing you can write as such. E 1 is 1 0 0, E 2 is 0 1 0 0 and so on. That is the standard basis we know. For matrices, E j k, what is E j k? In that matrix, the j kth element is 1, everything else is 0, right. So, how many such matrices are there? M cross n, right. They are linearly independent and generate everything. So, basically saying it is nothing but r to the power m n, right, standard basis of that, written as matrices, nothing more than that. Let us look at this thing, will come back to you in differential equations. Just want to, if you look at this equation, y double dash plus mu square x is equal to 0, is given that cos mu x and sin mu x form a basis of the solution space. So, what does solution mean? If I put y is equal to cos mu x or y equal to mu sin mu x as a functions, then they will satisfy this equation, right. That is okay. You can just check, okay, because when you differentiate, mu will come out, it will become sin, once again differentiate, it will become sin again, and so. So, they form, one will be plus sign, other will be giving a minus sign. So, that is solutions of, both are solutions, right. So, and this is homogeneous, right hand side 0. So, we just now seen that all, if where two solutions are there, their linear combination also is a solution. So, to look at the space generated by these two elements, all linear combinations, that is the solution space for this, okay. That is finite dimensional. So, every solution is obtained as cos and mu, linear combination of them. Are they independent? That is the only question. Then they will form a basis. They will form a basis if they are independent. So, that means what? If I take alpha times cos mu, x plus beta times sin mu x is equal to 0, that should say alpha is equal to 0 and beta equal to 0. Does that happen? Because again when you say right hand side equal to 0, that is a function, right. That means this equation is equal, this is left hand side is a function which is equal to 0 for every value of x. That is how you should understand that. If it is true for every value of x, I can put any particular value, say x is equal to 0. So, alpha cos mu x plus beta sin mu x is equal to 0 for x is equal to 0. What does it give me? Alpha cos 0 is equal to 0, right, because sin 0 is 0. So, what does that mean? Alpha is equal to 0, right. Cos 0 is 1, alpha times 1 plus 0 equal to 0. So, alpha is equal to 1. Similarly, you can take the value say equal to pi by 2, right. Then cos is 0, that term vanishes, we will get only beta times sin, right, or pi by 2 by mu, that value you can change, right. That is not important. So, sin can be made as 1 for a particular value, cos can be made as 0 and other way around. So, beta will be 0. So, that is linearly independent. So, this you will come across in when you are studying solutions of a differential equation, this will come back to you. How do you describe all possible solutions of a differential equation? You will look at the homogeneous part of it, you will find a basis for homogeneous part will give you a vector space, and you want to generate that vector space by describing the minimum number of independent solutions. So, this kind of things will come back to you. Okay. Let us look at one more example. Let us look at all polynomials of degree less than or equal to 3 with p 1 equal to 0. Let us discuss this. So, I am looking at the space is V, all polynomials p x belonging to R 3 such that p of 1, the value at 1 is 0. First of all, is V, so this is a subset of R 3 x, right. So, is V a vector space or vector subspace? First of all, we have to check whether it is a subspace or not. That means what? That means if p 1 and p 2 belong to V, does this imply alpha times p 1 plus beta times p 2 belongs to V, right? If that is the case, then okay. So, what does this mean? That means p 1 of 1 is equal to 0, p 2 of 1 is equal to 0, that is given to me. And what does this mean? If I have to check, that means alpha p 1 of V plus beta p 2 of 1, that should be equal to 0. But what is this equal to? This is 0, this is 0, alpha times 0 plus beta times 0, that is equal to 0, right. So, hence V is a vector space. In itself, it is a vector space, it is subspace of it. So, the claim is, look at the set 1 minus x, 1 minus x square and 1 minus x cube, that is a set S, is a subset of V, of course not equal to, right. Claim that this is a basis, this is a basis of V. So, what is to be shown? First of all, I do not know whether it is a subset or not, I should verify that also, right. So, let us look at in this, if I put x is equal to 1, this is 0. So, p 1 is 0, p 1 of 1 is 0, p 2 of 1 that is 0, p 3 of 1 that also is equal to 0. So, p 1, p 2, p 3, these 3 polynomials are right in V. So, that is not a problem. So, it is a subset. So, now the claim is that it is a basis. So, what is the first thing we should check? What are the two things to be checked? One, this set S is linearly independent, and second, it generates V. These two things to be checked. So, let us check one by one both of them. So, independence. So, let alpha times 1 minus x plus beta times 1 minus x square plus gamma times 1 minus x cube equal to 0, right. Let us say that is equal to 0. We have to show that alpha is equal to 0, beta is equal to 0 and gamma equal to 0. So, what does this mean? Implies, so this will be alpha plus beta plus gamma, that is a constant part of the left hand side, plus this minus, so minus alpha x, there is no x here, okay, plus minus beta times x square minus gamma times x cube equal to 0. What I have done? I just expressed left hand side as a polynomial, nothing more than that, because one polynomial equal to 0 polynomial, I have to see what are the coefficients of the left hand side. So, what does that imply? Alpha plus beta plus gamma equal to 0, coefficient of x minus alpha equal to 0, coefficient of x square minus beta equal to 0, coefficient of gamma minus gamma equal to 0, right. Comparing coefficients of like terms. So, implies alpha equal to 0 equal to beta equal to gamma. Is okay? Just using the fact that one polynomial equal to 0 means coefficient of each term must be, each power must be 0. Okay. So, that, so hence S is linearly independent. What is the next thing to show? It generates. So, claim S is equal to V. So, let us take a polynomial, let P x belong to V, implies P of 1 is equal to 0, right, and let us write P x is a polynomial. So, it will be of the form a 0 plus a 1 x plus V is of cubic, right. So, a 2 x square plus a 3 x cube. Is that okay? P is some polynomial with some coefficients a 0, we do not know what they are, we have to find them and express this with this property. I should check P is equal to alpha alpha times 1 minus x. So, P of x 1 minus x plus beta times 1 minus x square plus gamma times for some alpha, beta and gamma. We do not know what are they. Every polynomial in V should be expressed as a linear combination. I have to find, if possible, alpha, beta and gamma, right. So, what does it mean? If I have to find this, can I find alpha, beta and gamma? What is the right hand side? So, what do I want? P x is equal to alpha plus beta plus gamma. I am rewriting that thing again, minus alpha plus minus alpha x. So, what is the next one? Plus minus beta x square minus beta x square plus minus gamma x cube, that is P x, right. Is it okay? If I have to find alpha, beta, gamma, I do not know what they are yet, but if this is so, this must be equal to this. So, that means what? Now, what is the property of P given to me? P was in V. So, P of 1 of V is 0. So, P 1 P of 1 is equal to 0. What does that imply? Alpha plus beta plus gamma is equal to 0. What is coefficient of x here? Minus x minus alpha, and what is the coefficient of x in P? Right? Sorry, that should be 0. P 1 of B, that means a 0 should be equal to, see, P 1 of P of 1 is 0. This goes off, a 0 is equal to 0. So, this is equal to a 0. Is it okay? Yes, by the property. What is the coefficient of x here? A1. What is the coefficient of x here? Minus alpha is equal to A1 minus beta is equal to A2 minus gamma is equal to A3. Is that okay? See, if Px has to be a linear combination, then this must be true, right? So, when I write this as a polynomial, this is nothing but Px is equal to this polynomial, but this polynomial is also equal to, we have assumed is A0 plus A1 x plus A2 of x square plus A3 of x cube, right. So, coefficients of like powers must be equal. So, alpha plus beta plus gamma should be equal to A0, but the property is P of 1 is equal to 0. So, I get this equation, coefficient of x minus alpha. What is the coefficient of x here? A1. So, A1 must be equal to this, A2 equal to this is equal to this. So, that means what? I have found Px for Px, I have found alpha, beta and gamma in terms of, see, P is given to me, right. The polynomial is given to me, that means A0, A1, A2, A3 are given to me. I have to find alpha, beta and gamma in terms of A0, A1, A2 and A3. That was the problem, right. Then it will be a linear combination. So, what I have found is A0 is equal to 0, okay. A1 is equal to minus alpha, A2 is equal to minus beta and A3. That means, alpha is equal to minus A1, beta is equal to minus A2 and gamma is equal to minus A3, right. With that, so A0 is equal to 0, anyway that is 0. So, that gives me the values. So, what I have proved is that, let us come back to the example. So, this vector space P1 equal to 0, okay, is a subspace 1, and second, these elements belong to V. This is a subset of V. This is linearly independent, and every element is a linear combination of that, right. And all this is becoming possible to check because everything is finite dimensional. So, we are able to bring everything to a system of equations basically, right. For example, here it came to 3 equations in variables, right. We can solve them. So, that is the advantage of finite dimensional vector spaces. You can do computations with them. Okay. So, let us just for every vector, if in finite dimension, what is the advantage of finite dimension? We will close there. That means what? There is a ordered basis. Finite dimension means there is a finite basis for that, right. Given a basis, every element will have a combination, right. Every vector V is a linear combination of them. So, alpha 1, alpha 2, alpha n are known. That means, this vector which is in V, which is the abstract vector space, I do not know what is that, it will be polynomials, it will be functions or anything, but if it is finite dimensional, I can associate with that vector a vector in R n, if there is a ordered basis of n vectors in that, right. Is it clear? For example, in R n, the polynomials, right, of degree n, what are the bases? 1 x, x to the power n. So, for a polynomial p with those coefficients, what is the corresponding vector? A0, A1, A2 and An. It is vector of length n plus 1, column vector. Those are numbers. Though it was a polynomial, you get a vector associated with it, which is a number, right, which is a vector, numbers are there. So, that is advantage. So, this is what is we call as the coordinate of that vector, which may be abstract, and this can be put on a computer. So, computation becomes possible, and this association, that means for every vector V in the vector space, we are associating a vector in R n, if the basis is R n, right. There is n elements in the basis, and this association is very nice, it preserves everything. That means, if I take two vectors and take the coordinate, that is same as coordinates of the individual and added, and coordinate of the scalar multiple is that. That means what? Essentially, it says for all practical purposes, your vector space V, which is finite dimensional of dimension n, can be recognized as f to the power n. If it is a complex, c to the power n, if real, r to the power n. So, that is why finite dimensional abstract vector spaces are not difficult to handle, because we can transform everything to r n or c n via this association, by picking a basis which is ordered basis and writing the coordinates of that. What becomes difficult is when they are infinite dimensional, right. Okay. After defining vector spaces, what did we do? After having defined dimension, basis and everything, next thing was looking at maps between vector spaces, transformations, right. So, let us do that thing now. So, let us look at two abstract vector spaces V and W, they will be arbitrary vector spaces, right. Then a map between T and W is called a linear map if it takes a linear structure here to the linear structure there. That means, T of, if you add, take addition in the vector space V and take their images, that gives you the image as the addition there in W. So, this addition is in W, this addition is in V. T of V plus W is T V plus T W, and similarly scalar multiple of that. So, it preserves the linear structure, that is all essentially we are saying, right. It gives due regard to the linear structure. Addition goes to addition of the images, scalar multiple goes to the scalar multiple of the image. In finite dimension, we have seen everything was connected with a matrix, right. A matrix multiplication gave you a linear map, and the same is possible here, but let us give examples first. Look at all polynomials and look at the derivative. Take a matrix P or take a linear polynomial P and look at its derivative. So, it is a map, P goes to P dash, it is a map from polynomials to polynomials, it is a map from R x to R x, right. Derivative of a polynomial is again a polynomial, yes, calculus. Okay. So, it is a map from polynomials to polynomials and it is a linear map. What is the derivative of P plus Q? Your addition formula of derivative says the derivative of P plus derivative of Q. What is derivative of alpha times P? Again alpha comes out as derivative of P. So, differentiation is a linear operation, be it polynomials or be it you can take the space of all differentiable functions, that also is a vector space, on that also it will be a linear map. Okay. So, derivative is a linear map, and that is why they become important. Look at the polynomial, the map T of C or tau of C, that is P of, you take x and translate x by C scalar. Okay. In the domain you translate and then take the image. Okay. That is a map. Is it linear or not? So, what are you doing? P is the polynomial, P goes to Q. What is Q of x? Q of x is P of x minus C, right. If you take two polynomials P1 and P2, add them, P1 plus P2, what is the image of P1? That is Q1, that is P of P1 of x minus C. What is image of P2? That is Q2, that is P of P2 of x minus C. What is addition? That is same as Q1 plus Q2. So, that is a linear map. Translation in the domain is a linear map. Okay. Translation in the range, that is not linear. Okay. That is not mentioned, I think. No, we do not have that. What about multiplying by x? Take a polynomial P x and multiply by x. Is that a linear operation? X times P1 plus P2 is same as x times P1 plus x times P2, right, and scalar also comes out. So, that is linear. Okay. This is another important linear operation, that is integration. Like differentiation, integral of f plus g is integral of f plus integral of g, integral of alpha f, alpha comes out, right. So, differentiation and integration both are linear operations on respective spaces. Here the functions, what are the functions which should be integrable? right, then only it makes sense. So, for example, you can take continuous functions, all continuous functions are integrable. So, these are linear maps, and these are the maps, they are linear, and that is why they become important in higher mathematics. Okay. Now, just wanted to say a few things. Constant maps are the easiest ones to handle, right? Nothing changes, everything goes to a constant. Next are what are called, the next map, what are the easiest ones? Constant plus x, linear maps. So, linear maps are the next which are easiest to handle, and the next one are the non-linear ones which are most difficult to handle. So, most of the mathematics, applied mathematics, is going from non-linear to linear. You make approximations, try to convert whatever is non-linearity, approximate it by linearity. All of your numerical analysis will be that only, mostly numerical linear algebra, numerical analysis, all will be trying to convert everything to linearity, because linearity is easier to handle and apply. For example, if you take derivative, right, a curve is there and derivative is a linear approximation, nearby it becomes linear. That is why linear approximation, tangent line approximations become important in calculus, and they are the ones which are used in your calculators. How do you think you punch a key on the calculator, what is the value of sin 37.5? How does that give you immediately some value? What it does at the background, there is an algorithm which says replace this by tangent line approximation, linear, and calculate and give me the value. So, all algorithms, most of them are based on, there could be slightly better quadratic approximations and so on, but linear is the simplest one. So, these are linear maps, and of course, if it is a finite dimensional vector spaces, right, then every linear map will give rise to a matrix, ordered basis, like we have done it earlier, same, right. So, they are easier to handle. So, we will stop here today. Next time what we will do is see how the notion of angle, right, is taken over to abstract vector spaces, perpendicularity. Okay.